Good afternoon everyone. I am Chanda Devnar, one of the PMRF fellows. So I am the TA of this Retrosynthesis in Organic Chemistry course instructed by Professor Shamik Nanda from IIT Kharagpur. So in this class I usually discuss about some concepts which will help you to solve your assignments and to understand more about this topic. So in today's session I will discuss about protection deprotection, means how we can protect any functional group and how we can deprotect that again, and also we will discuss about some important cyclo addition reactions which you can apply for synthesizing some important chemical structure. Before that, in the last class I gave a homework to try, so let's try to solve that first. After that we will move to today's content. So what was the question? Which is the major product formed in the reaction sequence? So here they have given one diketone type of compound. In that they have added a base, that is sodium methoxide. It's a base, sodium methoxide, and alkyl bromide, that is the cyclohexanyl bromide. So this base is positively charged and this is negatively charged, so it can abstract proton. So in this structure, which is the most acidic proton? We have discussed about the ketonyl tautomerism in the very first class, and also after that also, like through aldol condensation and other reactions. So here, as these methylene protons are in conjugation with two carbonyl group, therefore they are more acidic. This is also in conjugation, but this proton has conjugation with at only one carbonyl group, whereas this two proton is in conjugation with two carbonyl group. So these proton are more acidic than that of this CH3 proton. So these are acidic. Because of that, this will abstract proton from here and generate this anion and generate this anion. What will happen? And now this will attack to this electrophilic center, and eliminate bromine or substitute bromine from this system and generating, which will be the product then desired. Now you have to, before tick the correct answer, you have to see it properly. See, both of them look similar, but which one will be your product? Obviously this C1. See, there is a one carbon less, but there have to be one carbon again. So it is attacking at this position, not this one. Okay, so there is one carbon less, so the correct option will be option C. Okay, I hope everyone understood. Okay, let's go to today's discussion. First we will discuss about protection deprotection, followed by cyclo addition, some cyclo addition type, different type of cyclo addition reactions. So what is protection deprotection and why we need to protect a group why and how to deprotect that again. So the more you, whenever there is a two reacting group, suppose in your substrate there are two functional group having similar kind of nature, like suppose one is aldehyde and another is ketone. Now you are adding some base, so it can attack to ketone and base both. So you have to, or you are adding some reducing agent, suppose you are adding LiLH4 or strong reducing agent, so it can reduce both the system. So therefore now what you want that at only one functional group react to your react in the reaction medium. For that scientists came up with this strategy where we can protect one of the group and react the another one, then after the reaction we can deprotect that group again. So what they, so by this one we can make the less reactive group in our participate in our reaction system. What I am saying, just the more usual way to reacting a less reactive group in the presence of more reactive one is use of protection. Suppose see in this substrate there is a carbonyl group and there is a ester center. There is a ketone center, this is ketone and this is a ester center. Now we know which one is more electrophilic. Which one is more electrophilic? Obviously this one is more electrophilic. This ketone center is more electrophilic. Now if you add a Grignard reagent, obviously it will attack to the center. Now suppose you want such product where you need this group to be reacted. You want this ester group to be reacted, not the carbonyl one, not the ketone one. Then what will you do? Then we came up with this protection. Then in that case, if you add some protecting group, obviously the more reactive group will react first. So with the protecting group, so in that case this group will react with the protecting group and will be protected first. Then now this part is free to the reagent to react. Then you can react this part and again after the reaction you can deprotect that again. So what they have done, see in this case they have added this diol type of system and have protected this ketone. Now this is not electrophilic anymore. In that case if you add a Grignard reagent, then it will react with this ester center generating this type of alcohol. After that if you add again acid, then this group will be deprotected and we will get our desired product. So by this protection methodology we can control the reactivity of the functional group. Like if we want, according to our necessity, like if we want our less reactive group to react first, then we will protect our more reactive group at first. After that we will make react our less reactive group. After the reaction is completed, then we will deprotect that again. So different type of protecting groups are there to protect different type of functional group. Like for all the functional group you can't use the same protecting reagent. So usually for carbonyl group, as you have seen, we use this acetyl ketal, like the dihydroxy type of compound, and this is whatever this is called ketal. This is called ketal. After protection, this is called ketal, and if it was aldehyde, it would call acetal. So for acetyl ketals for carbonyl group, silyl ether for alcohol, if there is a alcohol and you want to protect that from other reagent, then you can protect it with silyl ether. Benzyl ether for alcohol, tosylate or mesitylate for alcohol, acetyl group for amines. Now we have to deprotect. Every group can be deprotected by a different reagent. By this strategy also, if you suppose you have 2-3 protection, you have done 2-3 protection in a single reaction. Now you want to deprotect the functional group one by one, not in a single step. By this method, like there is selectivity in the protecting reagent and then by using different deprotecting reagent we can deprotect a functional particular functionality. Suppose the hydrolysis of acetyl-ketal with acid will deprotect the carbonyl group. If you want to deprotect the alcohol from the silyl ether, we have to add of any fluoride source. You have to deprotect the alcohol from benzyl ether. We have to do hydrogenolysis. If you want to deprotect acid from BOC or FMOC, if you want to deprotect the alcohol from BOC or FMOC, we have to add acid. If you want to deprotect from tosylate or methylate, we have to add some nucleophile. Here there is a list. You can take a screenshot of that also. Here I have shown like which type of protecting group and they after protection how they look, and which type of protecting group can be used for which type of functionality, and how they can be deprotected, and these are the protecting reagent and how to deprotect them. So I have compiled that. You can take a screenshot of this one. So let's go to the some question solve. So they have given a question. It came in GATE 2014. What will be the major product formed in this reaction? They have given this system. This is called glucose. You know. So they have given this one and added methyl sulfate NaOH, and in the second step they have added HCl and H2O. What will happen? So methyl sulfate is a strong methylating agent. It will methylate all the hydroxy group. In presence of Me2S4, all the OH will be methylated. All the OH will be now if you add HCl H2O, then it will deprotect the ether again. In presence of acid, the ether will be deprotected, but HCl is not that much strong to deprotect all the methyl. HCl is not that much strong to deprotect all the methyl center. In that case, only the anomeric OH will be deprotected. So here the anomeric OH is this one. So only this part will be deprotected. So our correct option will be option C. Okay. So just by this, like if you want free this anomeric OH only and protect all this OMe, you can take this strategy. Another question: identify the product of hydrogenation of the protected amino acid. Now in the list I have talked about like which group. There is 3 protection. See, OCOPH, that is benzoyl, CH2PH, that is benzyl, and there is a CBZ. So there are 3 types of protecting reagent. Now they are adding H2PD. Which of the group will be deprotected? So just by choosing the deprotecting reagent, you can deprotect selectively one functionality. So just think, there is a list. So just give it a shot. I'll just give 5 seconds. So in presence of, through hydrogenolysis we can depotate the benzyl group. We can depotate the benzyl group selectively. So in presence of hydrogenolysis we can depotate the benzyl group selectively. So all these group will be there, only benzyl group will be deprotected. So correct option will be option A. Okay, let's go to our next question. The major product formed in the following reaction. They have added this reagent. This is called DDQ. This is called DDQ. There is also 4 type of protecting group. One is benzyl, one is paramethoxybenzyl, one is this paramethoxyether, another is paramethoxyester. So which will be deprotected in presence of DDQ? So it has been seen in presence of DDQ only paramethoxybenzyl ether get deprotected. Paramethoxybenzyl. See, there is a difference between these two. This is not benzyl. There is one CH2 less. This is the benzyl. There is a CH2. So paramethoxybenzyl get deprotected selectively. So our correct option will be option D. Okay. So you have to look into this substrate correctly. Only benzyl. It has to be benzyl, not just paramethoxyether. It has to be paramethoxybenzyl ether. Paramethoxybenzyl, not just paramethoxy. Okay. Now just let's try this as much till now. Whatever strategy we have learned, based on that we'll try to solve this one. Alright, let's take a shot. We'll just go through the slides totally, then at last we'll come to this question again and we will solve it together. Okay, so next question is pericyclic. Next topic is pericyclic reaction. Actually we will mainly discuss about the cycloaddition reaction. So it is a part of a pericyclic reaction. The pericyclic reactions are 3 types. One is cycloaddition, next is sigma-topic reaction, another is electrocyclic reaction. So there, the one of the important type of cycloaddition reaction is Diels-Alder reaction. Most of you have heard about this. So what is Diels-Alder reaction? In the Diels-Alder reaction, a 1,3-diene react with a dienophile to form a 6-member ring add-on. 2 sigma bond and a pi bond are formed at the expense of 3 bonds, at the expense of 3 pi bonds in the starting material. So what they are saying, see, in this case what will happen, this will go here, letter, and this pi bond shifts. So just see, on the expense of this one, 2, 3. In expense of 3 pi bonds, how many new bonds are forming? 1 sigma bond, there is another sigma bond and a pi bond. Expense of 3 pi bonds, we are getting 2 sigma bond and a pi bond. So and forming a 6-member ring. So this is called Diels-Alder reaction. So a acyclic conjugated diene can react also. Here we have taken this acyclic diene, so, but there is a requirement. The diene to react, it has to be cis. Substitute, it has to be cis. Otherwise, this arrangement will not possible. If it is trans, this part will be far from this center, it will not be possible. The substituents in the butadiene molecule influence the rate of the cyclotration reaction through their electronic nature and by a steric effect on the conformational equilibrium. Bulky substituents that discourage the diene from adopting the cis-OH conformation hinder the reaction. If there is a group, such group, suppose this one, if it wants to take a cis conformation, what will happen? There will be huge steric interaction. Because of that, it won't take this seed conformation. This equilibrium will be shifted to the trans conformation. Whereas in this case, there is a steric hindrance, but this is quite less. In this case also, this appears as a cis form. So apparently 2,3-dibutylene is prevented from attaining necessary planar cis-OH conformation. This one, because of the high steric interaction. In contrast, 1,3-dibutylene, if it is but in this case, as there is no such steric interaction, it can get the cis-OH conformation and readily react with the malic anhydride to get our Diels-Alder adduct. Based on that, there is one question came in GATE 2019. The number of following diene that undergo Diels-Alder reaction with methyl acrylate. What is methyl acrylate? So methyl acrylate is this one. Alpha beta unsaturated ester. This is a methyl acrylate. So this can act as a dienophile. This part can act as a dienophile. So and all these 6, 7s are diene. So which of these will take part in a Diels-Alder type of reaction with this dienophile? Obviously, whichever is in the cis-OH form, that will be preferably take part in this Diels-Alder reaction. So in the whichever is the cyclic form, there is readily take. So this one will take part, obviously. Similarly, this one also, because this is cyclic system, so it is locked in its cis-OH conformation. There can be a steric interaction. They are locked, so it will not react. It will also not react. This is a steric interaction, but it will somewhat give a Diels-Alder reaction. It will give somewhat a Diels-Alder, because this, in case of butyl group, there is a huge steric interaction because of 3-methyl group, but here the steric interaction is less. Steric interaction is there, but it is less because there is a small methyl group. So this will also react. Similarly, in this case, these are already in cis-OH form, so this will also react. So how many of them? So the number will be 5. Okay, understood? If there is butyl, there is no chance of cis-OH conformation, but as they are methyl, so steric interaction is quite less. Because of that, it can take part in Diels-Alder reaction. So another question in GATE 2021. So what is the major product formed in the following reaction? So by seeing this diene and dienophile, you have come to know that it will be a Diels-Alder reaction, because all are 6-member ring. How they will combine to get a product? Now we have told that the group on the dienophile and diene also determine, as well as determine the steric bulkiness. It will also create an electronic effect. So this is a electron donating group. So it can move the electron density towards this side. While this is the electron withdrawing group, it can attract the electron density. So it will generate a delta positive charge at this position, whereas it will generate a delta negative charge at this position. So obviously a delta positive charge will try to combine with the delta negative charge, so this part will combine with this one, and we will get trimethylcyclyl. I am writing in a short form OTMS. We will get this one. Now in the second step, they have added aqueous acid. So in presence of acid, this will get in presence of acid, this part will get deprotected. Due to ketonal tautomerism, to generate this product. Now as these alpha hydrogens are acidic as they are adjacent to carbonyl group, so this will come here and undergoes a hydrolysis, giving us C as our product. C as our product. Understood? In presence of acid, so here we have combined the concept of Diels-Alder and protection deprotection. So by acid, both the OTMS and actually acid by both the ether center can be deprotected. So in presence of acid, both the ether will be deprotected, whereas the CN will be unaffected in the reaction medium. Okay. The next cycloaddition type, that is 2+2 cycloaddition reaction. So 2+2 cycloaddition reaction has found considerable use in synthesis, particularly for the formation of compounds containing 4-membered ring. The combination of two alkene leads to a cyclobutane ring, although most alkenes do not undergo a thermal 2+2 cycloaddition reaction with another alkene. However, many 2+2 cycloaddition reactions are carried out under photochemical condition. So the major product formed in the following intramolecular cycloaddition reaction. So what will be the major product form? So usually the alkene do not take part in cycloaddition reaction, but alpha beta unsaturated alkene are prone to take part in a cycloaddition reaction. So here there is alpha beta unsaturated alkene. So it can easily take part in cycloaddition reaction. So this will combine with this through a 2+2 cycloaddition reaction, giving us this as our product. So our correct option will be option D. So usually here you have seen that I have mentioned this top line. usually most of the alkenes do not undergo thermal 2+2 cycloaddition reaction, but in photochemical condition it can take part in a cycloaddition reaction, and alpha beta unsaturated double bond are prone to do that, so it will take in this way. Okay. There another type of cycloaddition reaction important. This has this name reaction has been mentioned again and again in your assignments. So just to get an idea what is DiMaio reaction, I am solving this one. So the DiMaio reaction is a photochemical reaction in which an enol of a 1,3 diketone reacts with an alkene, and the resulting cyclobutane ring undergoes a retro-Diels-Alder reaction to yield 1,5 diketone. So what they are saying, a 1,3 diketone will react with a tautomerase to this enol form, and then this double bond will undergoes a 2+2 cycloaddition with the alkene, forming this cyclobutane ring. Then it will undergoes a retroaldol type of reaction where this OH comes here and this bond breaks and it's open up and form this as our product. Now in case of acyclic system you can't see much difference, but if it is a so by this process what you can see, there is a incorporation of this alkene system in between these two carbonyl systems. See, there these two carbonyls are initially there. Now this alkene part just enters between them, increasing 2 carbon. So now if you want to increase the number of 2 carbon between two carbonyl group, what you can perform this DiMaio reaction. In case of cyclic system, if you want to increase the ring member, in that case also you can use this DiMaio reaction. So if we go into the mechanism part, here also just by it will undergo the cycloaddition type of reaction, form 2+2 cycloaddition reaction, forming this cyclobutane. Then it will undergo the retro-Diels-Alder reaction, forming this 1,5 diketone. Now head to tail alignment gives the major product, like if as in this case this is the delta positive center, whereas this is the delta negative center. Because of that, if we combine the positive negative side, that will give us our major product. But if we join in an alternative way where this is positively charged and this is also positively charged, and if you want to combine this side to this one, this part will give us our minor product. Okay, this is also why what we have discussed in case of Diels-Alder reaction. We will get the major product where the electronic effect supports our connection. So here, as this is beta carbon, it is a delta positive charge, but here as it is a alpha carbon, this is delta negative. So this combination will always give us our major product. So one question is given. This is based on this DiMaio reaction. Just give it a shot. Then we will solve it together. So what will happen here? First it will undergo a 2+2 cycloaddition. then it will go under. Will form this 8,5 fuse cyclic ring in the reaction medium. Okay. So I am giving this as homework. Just try. Then we will solve this in the next class. I have shown the product also. We will solve it in the next class. Now let's go back to our question we left there. We'll give a forward synthesis of this compound. So for the idea they have given that we have to go this up to this. So just let's try. What we can do? Suppose if we just reduce this carbonyl compound. Just to get our desired one. Now what we can do? So this is a silyl protecting group. If we deprotect this, suppose this was OH. this, we protect this one with benzyl. This gives us OBN, and if it was a epoxide, okay. So here this way you can plan the retrosynthesis. Let's go to the forward synthesis, what we are planning. So let's start with this alcohol, allylic alcohol. Now we have to see that how I have planned. Now here we know that if we add MCPBA and if there is a OH group, it will always form the epoxide from the plane of where the OH group is. That's why we are just protecting it first and making it OBN. In case of ether, that is not possible. So if we protect it and make it OBN, like benzyl bromide, and NaH. Now if we add MCPBA, what will happen? Now if we add MCPBA, this will undergo epoxidation. But as this is ether, the epoxidation obviously will be the opposite plane of this ether group. There is no such hydrogen bonding will take place here. So it will form this one. After that, what I have done, I have opened this ether. So as it is above the plane, so the incoming OMe group will come from the below the plane. So if we add OMe minus, it will come from the below the plane. Now if we deprotect it, if we protect it again, now this both are, one is OBN, another is OMe, so only one OH is available. Now let's protect it with TBDMSCl, tert butyl dimethyl silane. TBMSCl, then it will give us this ether, silyl ether. Now if you add H2PD, there are three protecting group. One is methyl ether, one is this silyl ether, another is benzyl. All the three are ether, but you want to deprotect a single ether, that is the benzyl ether. So here you can see the concept of protection, deprotection. They all are three are ethers, but you want to deprotect specifically this benzyl ether. Now in this case, if you add H2P, that's why we have protected this OH first with benzyl. If you would protect with something different reagent like methyl, or then there will be no discrimination, and in that case both the center will be deprotected at the same time. So you have deprotected. So in while choosing the protecting reagent also, you have to be concerned by the other groups which are present in your molecule. So it can't affect others. I am not writing a full the OT, and next is this. I am not writing this OTVDMS completely. OTV, and there is OME. We are almost there. Now if you just perform oxidation, by simple PCC, then only the alcohol will be oxidized, forming our desired compound. So here you can see, by using the concept of protection, deprotection, how we can plan the retrosynthesis of a compound. Okay, understood. So what we have learned today? So we have learned about deprotection, how we can protect a single functional group, and by using a specific deprotecting reagent, how we can deprotect that. Then we discussed about all the different type of protecting reagent. Suppose in case of ketones and aldehyde, we will use this protecting reagent which forming acetal. This can be deprotected by H plus. For simple alcohol, we can use this trialkyl silyl, which can be deprotected by H plus, that we have done, or fluoride source H plus, or any acidic source or any fluoride source. Then for another alcohol, we can use THP, that is tetrahydropyranil. It can be deprotected by H plus. Next, by benzyl ether, by using it can be deprotected by H2PD selectively. Next is methyl ether, that can be deprotected by BBR3. Next is tertiary butyl ether. Tertiary butyl ester, it can be deprotected by strong acid. Next is CBZ, which is used for amino acid mainly, can be deprotected by HBr or H2PD. Further, the BOC, which can be deprotected by H plus. Next, FMOC, that can be deprotected by base. Then we have discussed one question, like how by using one protecting reagent we can protect all the hydroxy group, and the protecting reagent only deprotect only one center. Then we have discussed about this one. Actually CBZ can deprotect both the centers, so our correct option is C. No. correct option will be option D. CBZ can depotate, H2PD can depotate both the CBZ and benzyl. That's why our correct option will be option D. H2PD can depotate CBZ as well as benzyl. So our correct option will be option D. So just if you have to remember which group can be deprotected by which reagent, otherwise there will be a confusion. So DDQ can be deprotect paramethoxy ether. Then we have drawn this retrosynthesis of this compound. Next we have discussed about some cycloaddition reaction followed by Diels-Alder reaction, then how the stereoelectronic effect controls a reaction. Then we discussed one of the previous year question and how we can determine the electronic effect for the connection. Then we have discussed about 2+2 cycloaddition reaction and one example from there. Then we discussed one of the important name reaction, that is D-Mayo reaction, which has been discussed in our assignments multiple times. Then how we can determine the product. This is basically a reaction of combination of 2+2 cycloaddition and a retro-Diels-Alder reaction. Then we have discussed one question from there, and I have given one question as homework so that you guys can try to get an idea. So this much for today's class. Thank you everyone. I hope it was a nice experience for all of you. We'll meet in the next Sunday at the same time. If you want to get an idea about my previous classes, the videos have been uploaded there. You can go and check. So thank you everyone. Have a nice day. Good afternoon.